blue lines at dawn. A spectrograph screams to life as 3I/Atlas slides into the slit. Faint, icy vapor lines spike where nothing should be, hinting at salty, ammonia-laced spray. The control room goes quiet. Someone just shouted ocean, and no one wants to be the first to breathe wrong. For a heartbeat, the world is all pixels. A row of scientists leans forward like synchronized swimmers about to dive. The display is a night skyline of data, sharp blue peaks rising where the spectrum should be smooth. Someone's pencil stops tapping. Someone else mutters the kind of word that only appears when careers pivot. The object on our screen is not just shedding gentle comet breath, it is coughing up the chemical perfume of a world that once knew tides. We start replaying the last minute, as if a cosmic dash camera recorded it. The telescope tracked perfectly. The guiding star behaved. Then our visitor slid into view, small, stubborn, and fast, pulling a whisper of vapor behind it. The spectrograph, usually a stoic librarian of light, turned gossipy. Specific lines brightened, the ones that say, "This is not plain water. This is water with friends." The most delicate spike suggests ammonia, the universal antifreeze, chemistry's invitation to a winter party. Another bump is the kind of shape you see when salts have been liberated from a briny prison and flung into sunlight. This is not drama for drama's sake. This is physics, wearing glitter. The room exhales in staggered breaths. Monitors hum. Coffee goes cold midair. The team lead, who laughs like an avalanche only when the data demand it, says very softly, "Again, we run the next exposure." The blue lines return, a little stronger, as if the object has heard us and is clearing its throat for a speech. That second confirmation is when the joke lands. Either we have found a visitor soaked in ocean memory, or the universe is pranking us with the world's most expensive practical joke. The cosmos has a sense of humor, but it rarely wastes photons. A junior analyst, cheeks flushed with the suddenness of having a front row seat to history, starts chasing the calibration files. Everything gets checked. The dark frames are clean, the flats are impeccable, the wavelengths match the lamps. If this is instrumental, it is an instrument with taste. The lines fall exactly where molecules must sing if they have been ripped from a cold solution and set free as a sunlit mist. They are not bold, not theatrical, but confident, like a whisper that somehow carries across a crowded room. If you have spent years staring at spectra, you know the difference between noise and narrative. Tonight, the narrative is loud enough to hear with your bones. In my head, an image forms of some faraway crust cracking, just enough for a pocket of brine to meet vacuum. The pressure drops, the liquid flashes into vapor, and the dissolved cargo comes along for the ride. The ratio of components, traces of ammonia balancing the water, the hint of ions that once made a salty soup, tells a story about temperature, about rock that shared its minerals with water over a long friendship. You cannot fake that with dust. Dust is messy. Brine is opinionated. Someone finally says the word again, cautious this time, like a diver testing a frozen lake. Ocean. The syllables float in the recycled air. Not a surface ocean that glitters and storms, but the quiet kind that lives beneath ice, shielded from starlight, warmed by a rocky heart. We have seen these seas in our own neighborhood, spraying from the flanks of one small moon and hiding under the face of another. But this visitor is not ours. It is a postcard from a system we have never met, stamped with chemistry and delivered by chance. There is a strange intimacy to this moment. We are smelling someone else's weather from across interstellar space. We are tasting, with instruments, a world that will never know us, that will pass and fade and never look back. The numbers on the screen feel like an introduction. Hello, we have salt. Hello, we have ammonia. Hello, we have water that learned to keep going when the cold arrived. If there is a sacred ritual in astronomy, it is this. You bring light, we bring patience, and together we extract meaning. Tonight, meaning arrives laced with brine. Outside, dawn smudges the horizon, and the telescope dome breathes like a sleeping animal. Inside, the team splits into two species: the celebrators, who grin with the reckless smile of people who just met a miracle, and the skeptics, whose joy only blooms after every trapdoor has been stomped on. Both are necessary. Discovery is a relay race where the baton is excitement wrapped in doubt. We pass it back and forth until the pace feels right. We cue a sequence to watch how the chemistry changes as the object rotates. If the blue lines rise and fall with a rhythm, we will know there are active vents, not a uniform haze. If different exposures emphasize different ingredients, we will know we are catching different faces, each with its own geologic gossip. The idea that we might map an alien ocean's habits from a series of spectral breaths feels absurd and yet perfectly sensible. Science is just curiosity with a time management problem. Through it all, humor sneaks in like an old friend who knows how to sit quietly. Someone writes on the whiteboard, "Dear Universe, thanks for the salt." Someone else adds, "Please include fries next time." The joke lands. We laugh because it is safer than shouting, and because even the biggest moments are human-sized when you are trying not to spill your coffee on a priceless keyboard. There will be press releases later, and reviews and papers that grow dense and thorny. There will be arguments about alternative explanations that are exotic and clever and probably wrong. There will be nights when the object is too faint, and mornings when the cloud cover wins. For now, there is just this crisp blue handwriting on the screen and the shared knowledge that we have heard a far ocean breathe out. Next, we will rewind to the alert that started this chase and the realization that our soggy traveler came from far beyond our backyard. Chapter 2. Who invited an interstellar snowball? Who invited an interstellar snowball? We rewind a few days. Discovery alert, orbit fit, and the moment the team realizes this visitor isn't local. A quick primer on why interstellar travelers are rare and why this one brought chemistry that sounds like it packed a lunch from a very wet kitchen. The alert did not leap. It pinged. A small, polite message threaded through the night's inboxes from a wide-field survey that spends its evenings catching everything that moves, from responsible asteroids to dust motes with attitude. The candidate looked ordinary at first. Faint, bluish, sliding against the starfield like a snail with ambition. It was the kind of detection that usually earns a shrug and a coffee refill. But the tracklets, those tiny breadcrumb positions across the sky, were too straight and too swift for comfort. A few observatories chimed in with follow-ups, and the dots started connecting themselves into a path with a personality. The object was not sauntering. It was doing a brisk interstellar power walk. Orbit fitting is a craft that blends patience with a love of difficult puzzles. You take positions on the sky, measured to absurd precision, and you ask the universe what path through space would make these dots line up like this. At first, the software offered the usual, a long, stretched oval that would keep our visitor tied to the sun, maybe looping back in a few million years to say hi again. Then more data arrived, and the oval misbehaved. It kept refusing to close. You could almost hear the orbital curve clearing its throat and saying, "I will not be staying for dessert." The numbers whispered a verdict in plain language. This thing is unbound. It came from elsewhere and will return to elsewhere. In the secret slang of orbital mechanics, it carried souvenir speed even if you escorted it far from the sun. Translation: foreign guest, no forwarding address. You could feel the room's temperature change when the team lead read that out. Every mind rewound to the handful of times we have had a visitor from the great outside. They are legendary because they do not happen often. There are reasons. First, stars cling to their toys. It takes a brutal kind of celestial pinball to fling a chunk of ice and rock so hard that it breaks up with its star and never looks back. Second, space is not a crowded highway. It is a mostly empty desert. Even if thousands of such travelers are wandering, the odds that one wanders right through the tiny keyhole of our telescopes during the narrow window we are looking is small. And third, until recently, our planetary neighborhood watch wore bifocals. We did not have enough all-sky, all-night eyes to catch the quick, the faint, the shy. Only in the past few years have we started sweeping the sky with a kind of relentless attention that turns chance into routine. The universe has always been dramatic. We only just installed better seating. So yes, rare, but rarity is not the whole plot. This snowball had a voice. Even before anyone looked at the subtle fingerprints of its breath, there was a whiff of personality in the way it brightened as it approached sunlight. It did not act like a dry, baked rock. It behaved like something with pockets. Imagine a traveler who wanders into your kitchen after a long road trip and empties their coat, a salt shaker, a bottle labeled "Do Not Freeze," a handful of mineral confetti that says, "I visited a place where water and rock hung out for a very long time." That is not what you expect from random rubble. That is what you expect from a body that once lived in a cooler outer realm, where ices grew fat and patient, and interiors learned slow tricks. Why bring such a pantry? Because not all small worlds are simple. Some of them begin as shy lumps of ice and dust beyond their star's frost line, and then discover, to their surprise, that their insides can warm up. Radioactive elements are tiny space heaters. Tidal tugs are slow massages. Both can melt pockets inside an icy shell. When liquid meets rock, it is not a quiet date. Minerals dissolve, balances shift, and the water becomes something more than water. It becomes a solvent with opinions. If that little world later fractures, by impact, by stress, by the capricious tantrums of temperature, those seasoned liquids can migrate toward the surface. If the world loses a fight with a giant planet and gets punted into freedom, those same ingredients are sealed inside as time capsules. Our guest looks like one such capsule that cracked open just enough to scent the air. But do not imagine a picturesque ocean beach. Picture instead a labyrinth beneath ice, a set of exchange counters where water barters with rock and carries away tiny receipts, ions, buffers, traces of molecules that do not mind the cold as much as we do. Over ages, those receipts can freeze into layers, like the sediment at the bottom of a very patient kettle. Interstellar travel is unkind to superficial layers. Micrometeorites, sandblast, starlight bleaches, cosmic rays scribble, but deeper down, the pantry stays preserved. An impact chip, a thermal stress, a careless cosmic pothole, and suddenly a pocket vents. The kitchen door swings open and the smells rush out. Of course, none of this would matter if we could not spot travelers at the right moment. The trick is timing. Interstellar visitors are fast by local standards, but they only get chatty when the sun warms them. That gives us a small window when they are both bright enough to notice and close enough to interrogate. Miss that window, and you are left waving at a tiny dot that refuses to tell you where it has been. Catch it, and you are rewarded with the rarest kind of gossip, an ingredient list from a kitchen we did not build. The first time you realize you are reading such a list, it feels like opening a neighbor's cookbook and finding your grandmother's handwriting. No one rang a dramatic bell the night the orbit fit, tipped from bound to unbound. The confirmation came as a string of quiet messages, as plots that stopped pretending, as two separate codes arriving at the same conviction from opposite angles. The team's group chat cycled through disbelief, caution, and the kind of restrained joy that scientists practice so we do not spook the data. By morning, the designation had updated to reflect its foreign citizenship, and our scheduling board looked like it had been tackled by a stampede of requests. Telescopes are time machines, with jealous waiting lists. Suddenly, everyone wanted a turn. If you zoom out, the comedy of it all is lovely. Somewhere in another system, long before our species learned to roast marshmallows, a small world acquired a taste for seasoning. It was then yeeted. Yes, a scientific term in spirit, if not in journals. across light years, wandered into our porch light and proceeded to act like a house guest who not only brings snacks, but insists you read the label. The universe remains the most chaotic chef, but even chaos leaves crumbs. Next, we will trade sky paths for light's secret handwriting and show how a beam split and stretched becomes a page where molecules confess in exquisite detail. Chapter 3, Spectral Whisper. Chemical Shout. Spectral Whisper. Chemical Shout. How light becomes a barcode. Absorption, emission, and the telltale signatures that point to salts, organics, and dissolved gases. Jargon gets a makeover. Photons are interns carrying gossip from a cosmic water cooler. Take a ray of light and stretch it until the colors fan out like a deck of cards. At first glance, it is just a rainbow with good posture. Look closer, and you will see tiny bites missing, hairline scratches, where certain shades have gone on break. Those are not accidents. They are the calling cards of atoms and molecules. Every kind of particle has favorite dance moves, energies it will happily absorb or release. When that happens, a specific color vanishes or flares. The result is a pattern of bright and dark lines that, once you learn the alphabet, reads like a confession. If you have ever watched a detective show where the lab tech squints at a smudge and says, "peanut butter," you know the vibe. Spectroscopy is that, but with more vowels and fewer sunglasses. Let us start with absorption, this art of polite theft. A photon passes by a molecule and hears, quite literally, "I will take that." If the photon's energy is exactly the ticket price for a molecule to shimmy into a new vibration or rotation, it gets swallowed. On our stretched rainbow, that looks like a notch one narrow color that arrived at the party and then ghosted. Stack enough of these notches and you have a barcode. Switch to emission and the molecule is the one paying the tab. After getting excited by sunlight, by collisions, by a bad influence, it calms down by throwing a photon back into the world at a very particular shade. Those show up as bright hairlines against dark backgrounds, as if the night itself developed freckles. Absorption or emission, the message is the same. This is who I am, and here is the exact energy that makes me wiggle. Now we bring on the molecules that haunt chilly, gassy places. Salts, when they are free-floating as ions or tangled into tiny aerosols, imprint broad, textured features, like brushstrokes rather than pinstripes. Organics, the catch-all for carbon-based molecules with personality, prefer forests of narrow lines spread across the red and infrared, each one tied to a different stretch or bend. Dissolved gases that escaped from a solution carry rotational and vibrational signatures that cluster in familiar neighborhoods of the spectrum. It is like walking through a city and recognizing districts by smell alone. Bakery Street, Coffee Alley, someone is grilling Boulevard. Give a spectrograph enough resolution and patience, and the city map emerges. Resolution deserves a quick curtain call. Imagine trying to read a barcode with foggy glasses. Low resolution smears the lines into polite blur. High resolution snaps them into place so you can count the stripes between the stripes. But sharpness is not everything. You also need signal. The difference between "I think I saw something" and "I would bet my lunch on it." That is where integration time helps. You let the light accumulate, like filling a rain gauge during a Tuesday-long drizzle. By the end, shy features step forward. Patience is a machine that converts faint whispers into usable sentences. What about line shapes? Those are the gossip tone. A narrow line with crisp sides says the gas is chilly and relaxed, with particles moving at modest speeds. A broadened line hints at heat and chaos, where motion dopplers the color into a slightly wider smear. A split line, ever so delicate, can betray a magnetic field or a pressure effect that jostles energy levels. Even asymmetry has meaning. Sometimes one side of a line is a little taller because the source is drifting, and the drift shifts color just enough to tip the balance. In short, lines do not only speak, they emote. The clever part is matching these emotions to specific suspects. we do that with libraries. In labs, people put known gases, aerosols, and condensed materials through their paces and record how they absorb and emit. That catalogue becomes our Rosetta Stone. When a mysterious spectrum shows up, we cross-reference. Do these wrinkles at long red wavelengths align with a family of carbon chains? Do those humps in the near-infrared echo hydrated minerals turning their shoulders to the light? Is that delicate ladder across the far red the hallmark of a dissolved gas escaping a liquid and telling tales mid-flight? When two or more patterns overlap, we peel them apart with models, like unmixing paint after an enthusiastic toddler stirred the palette. And then there is the party trick, fluorescence. Some molecules, especially complex organics, take in blue or ultraviolet light and then glow back at gentler shades. It is their way of saying that was intense and returning the extra energy in a friendlier form. And a spectrum, this can look like a gentle hill rather than crisp lines, a glow that rides above the background. Catch that hill rolling on and off as the source rotates, and you learn not just what is there, but where it lives on the surface or in the surrounding plume. Let us translate a little jargon while we are here. Continuum is not a philosophy podcast. It is the smooth part of the spectrum that everything else rides on. Baseline is not a musical groove. It is the quiet level you subtract, so the features are honest. Noise is the universe clearing its throat, which you learn to ignore without becoming rude. Calibration is the etiquette class that teaches your instrument which shade of red is actually red. And photons? They truly are interns carrying gossip from the cosmic water cooler. They have no opinions, only itineraries. But when enough of them show up with the same story, you take notes. A final detective move, ratios. Absolute brightness can be slippery because distance and dust get in the way. Ratios between lines, however, are sturdy. Compare one fingerprint to its sibling, and you learn about temperature, density, even the relative abundance of one species to another. Switch the ratios with time, and you see chemistry evolve in real time, as if the source is changing recipes while you watch. That is the magic. Light becomes not only a list of ingredients, but a record of the kitchen at work. Next, we step from the rainbow back to the plume itself, pulling apart jets, vents, and the choreography that decides which flavors escape first and which bide their time. Now continue to how to read a coma without falling asleep, from coma to nucleus, sublimation, jets, and what escapes first as the object warms. We follow the plume physics that separates surface frost from brines, hiding deeper, like a geyser with stage fright. Stretch it into a full 700, 800-word deep dive with zero repetition from any future or previous chapter. Chapter 4, How to Read a Coma Without Falling Asleep. How to read a coma without falling asleep. From coma to nucleus, sublimation, jets, and what escapes first as the object warms. We follow the plume physics that separates surface frost from brines, hiding deeper, like a geyser with stage fright. Picture the nucleus as a dim, lumpy iceberg no one invited to the spotlight. It tumbles through sunlight, crusted with ancient frost and stitched with seams where heat once bargained with cold. Around it swells the coma, a ghostly atmosphere born fresh every moment as ices whisper into vapor and dust hitches a ride. The coma is not a fog in the usual sense. It is more like a busy train station where every molecule buys a one-way ticket outward. Read it correctly, and you can tell who boarded first, who missed the train, and who arrived from a hidden platform. The plot starts at the surface when dawn crawls across the nucleus. The first responders are the most skittish ices, a touch of light, and they leap. They do not negotiate. They vanish straight into gas and slip between grains like impatient shoppers. This is the frost flash, a brisk early rush that creates a thin veil hugging the surface. It fades as quickly as morning breath, leaving behind a chill crust that has lost its fluff and gained a little backbone. Next comes the slow warming, Sunlight does not melt its way inward like a blowtorch. It seeps. There is a shallow depth where the day's warmth penetrates before the next night steals it back. In that thin layer, ices nested between grains begin to sublimate from within. They puff into tiny pockets, raise the local pressure, and squeeze through pores toward any crack that offers an exit. Think of it as popcorn popping in ultra-slow motion. Some kernels expand and escape. Others jam against their neighbors and wait for a better angle. Jets ignite where the plumbing aligns. A crack taps into a pocket. The pocket taps into a honeycomb. And suddenly, you have a nozzle. Gas rushes out. Pressure drops behind it. And more gas feeds the flow in a self-reinforcing whoosh. Dust gets pulled along if the drag beats the stubborn forces holding grains together. The finest particles go willingly, streamlining into a bright beam. Larger chunks need a stronger tug, and often tumble out later, like latecomers, elbowing onto a crowded bus. From a distance, the scene looks surgical, narrow pillars of light against the black. Up close, it is organized chaos with excellent choreography. Here is where plume physics plays favorites. Surface frost delivers quick, clean gas with a modest dust garnish. Deep reservoirs deliver mixtures that have had time to stew. The pathway matters. If gas travels through a long, narrow crack, it cools as it expands and can condense some passengers back onto the walls, leaving them behind like luggage that failed the overhead bin test. If the crack widens, pressure falls faster, and the flow accelerates, flinging more material outward. The jet's profile, its brightness, its width, its tendency to flicker, betrays the plumbing geometry, as surely as a whistle tells you how a kettle is built. Rotation turns this into theater. As the nucleus spins, jets wink on when their source faces the sun and dim when the light slips away. Some persist longer because the subsurface stayed warm after sunset, like a stone that remembers noon. Others act like nervous geysers with stage fright. They sputter, gather courage, and then erupt in a brief flourish before retreating. Stitch together a few rotations, and you get a map of hotspots, cold shoulders, and places that do not care about time, because their reservoirs are fed by deeper heat. Dust tells its own subplot. Close to the surface, grains zip along with the gas, a tight core of particles moving as one. Farther out, the gas thins and the dust keeps coasting, peeling away into fans and shells. The smallest grains scatter sunlight ahead of the nucleus and make it look haloed when the phase is right. The bigger specks gravitate into tails that remember yesterday's winds. If you squint, the coma looks layered, because it is. Fresh gas near the core, mixed gas beyond, the elders farther still, all drifting outward while the nucleus shrugs and cooks up the next batch. There is also the matter of back pressure. If vents clog by falling pebbles, by recondensed frost, by grains that wedge themselves like over-eager corks, the pressure behind the blockage rises. Eventually, the seal fails. Sometimes gently, sometimes with a pop that sends a spray of debris and a fresh jet that makes observers mutter breakfast words. These outbursts paint arcs into the coma as new material interpolates into the older flow, and the structure suddenly looks like a tree ring that forgot to be subtle. Reading a coma means listening for these rhythms. Is the near nucleus gas dense and calm, or thin and frantic? Do the jets stay put, or do they migrate as the plumbing evolves? Are there pulses that repeat with a spin, or surprises that respect no schedule, combine timing, brightness, and geometry? And you can sort the contributions. A morning, frost breath here, a noon plume there, a midnight leak from a layer that never quite cools. No single measurement gets you the full melody. You need the chorus across hours and days. Not everything escapes freely. Some gas condenses on the night side and waits for a second chance at dawn. Some particles charge up under sunlight and feel the local electric field tugging them into odd directions, adorning the coma with subtle veils, like scarves caught in a breeze. Even the nucleus itself responds to this steady exhale. Each jet's shove is tiny, But together, they nudge the path, a whisper of thrust that can twist the spin or curve the trajectory. The traveler is literally steering on its own breath, a cosmic paddle boat with no intention of being polite about it. What separates surface frost from deeper brines is hesitation. Frost is a sprinter. Quick start, quick fade, clean signature. Deeper sources are marathoners, late to the line, reluctant at first, then stubbornly consistent once they find their pace. When you see a jet that endures past sunset, that is a clue the pipeline remembers warmth from below. When a plume carries larger grains or flickers with pressure beats, you are likely tapping a pocket that argued with its lid before winning. The geyser with stage fright keeps peeking through the curtain until the applause, meaning sunlight and pressure, grows irresistible. By the time the coma fills the field of view, it no longer looks sleepy. It looks alive, patterned by plumbing and rotation, tuned by grain sizes and thermal memory. You read it the way a sailor reads the surface to guess what currents twist below. And once you can tell a sprinter from a marathoner, you can start asking bolder questions about what the hidden reservoirs were doing, long before the show began. Next, we turn from flow and flicker to the case file of flavors, weighing whether certain spectral bumps belong to innocent dust or a deeper, seasoned brew that changes the stakes entirely. Chapter 5, The Salty Plot Twist. The salty plot twist, the first big debate. Can simple dust mimic salt signatures, or are we really tasting brine? Lab analogs, false positives, and the uncomfortable meeting where someone says, table salt, and someone else says, prove it. It begins with a graph pinned on the screen, like a butterfly. 2 shallow swells in the infrared, a delicate wiggle in the red, and a modest rise where, according to several very opinionated papers, halide-bearing aerosols like to show off. A hand at the back, new hire, bold voice says, that looks like table salt. A chair squeaks, someone coughs in academic. Another voice, cool as liquid nitrogen, prove it. Salt is a crowd pleaser because it is a storyteller. Halite and its cousins bend light in distinct, lumpy ways when they are powdered, frosted, or floating as microscopic specks. But dust is a professional impersonator. Give silicate grains a bit of weathering, a veneer of frost, or a coat of sulfates, and they can fake the same curves with alarming grace. Our job is to tell the karaoke from the original track. Cue the first slide in the gauntlet, particle size. Spectral features from salts change shape depending on grain diameter, in a way that is not identical to ordinary rock powder. Very tiny salt specks tend to broaden and smooth their humps. Slightly larger ones sharpen and shift. Silicates behave differently. Their resonances are finicky about lattice structure and less eager to migrate with size. If we can pin down a consistent grain size trend across a range of angles, the mask may slip. The counter-argument: the coma is not a tidy lab tray. It hosts a confetti of sizes all at once, and averaging can make unique features look boringly generic. Dust, in short, wins by being messy. Next slide, hygroscopicity, the love of water. Salt particles act like tiny extroverts at a humid party. They drink from the air and change their optical mood as they do. In a vacuum, they shed that water and sulk. If the features strengthen when the plume is denser and fade in leaner moments, that is a wink from hygroscopic grains. Silicates, even when hydrated, are less dramatic about it. The pushback? Temperature can mimic the same behavior. Warm a mixture and lines relax. Cool it and they perk up. Are we watching thirst or thermostat? Enter the lab crew, rolling in carts like a pit stop team. They have been cooking analog dust for months. Ground basalts, powdered halite, sulfates, exotic chloride hydrates with names that sound like luxury soaps. They chill them, bake them, beam them with lamps that mimic sunlight, and puff them through vacuum chambers to measure how the features evolve as grains loft and settle. The best moments are quiet, when a curve from the chamber overlays a curve from space and the room forgets to blink. But analogs come with fine print. Real may add coatings mid-flight, accumulate electrostatic charges, and collide gently in slow motion. Even the most heroic chamber cannot rehearse every improvisation. We make a detour through polarization, the way scattered light acquires a preferred wiggle direction after meeting particles, salty aerosols and rock dust, polarize differently as a function of angle, because their surfaces are smoother or rougher. Their refractive indices more or less dramatic. Measure that polarization curve alongside the spectrum, and you get a fingerprint with two hands. The objection arrives on schedule. Polarization loves to be ambiguous. Add a sprinkling of fluffy aggregates, and the curve slides toward rock, even if salty beads are present. Subtract them, and the curve looks exotic again. It is less a fingerprint and more a horoscope. Someone suggests sodium and potassium lines, bright, narrow emissions that sometimes flutter above comets like neon signs. If we see those, surely we have salts. The room shakes its collective head. Those lines can come from many sources. Sputtered from grains by sunlight, liberated from minerals by heat, or teased off surfaces by gentle micrometeoroid taps. They shout, there were alkali atoms here. Not this came from brine, great for headlines, lousy for provenance. We open the folder labeled false positives. Inside, hydrated silicates that masquerade as sulfates if you sample too coarsely. Organics that add a low, rolling continuum glow and make everything look slightly salted. Instrument scattered light that raises the baseline in the exact neighborhood you are about to claim as a chloride chorus. There is also the villain named telluric, the Earth's own atmospheric fingerprints that sneak into data if you do not subtract them with priestly care. A junior analyst produces plots showing how a whisper from our atmosphere could counterfeit a subtle hump if the calibration star had the wrong mood. The room votes to redo the subtraction. The room always votes to redo the subtraction. The prove-it camp brings statistics armed with hats. Model A, plain silicate dust plus carbonaceous fluff. Model B, the same, with a sprinkling of salts. We let a Bayesian referee tally which model earns its keep once you pay the fee for extra parameters. No cherry picking. The evidence score counts grace, not swagger. The first pass favors the salted model, but only just. Like a judge who says technically yes while grimacing. The second pass, with a refined particle size distribution and a more realistic temperature profile, nudges the salted model ahead by a respectable margin. Not a landslide, but enough for raised eyebrows and a few involuntary grins. Then comes the meeting. The agenda says feature attribution, but everyone knows it is the salt trial. The table salt comment returns for an encore. A senior colleague counters with a calm list of ways rocks pretend to be pantry items. Someone sketches a plume's life cycle on the whiteboard and circles the phase where brine droplets could shatter into aerosols, tiny spheres with optical behavior that is hard for irregular dust to counterfeit. Another pointer arcs to the timing. The features peak when the rotation brings a certain longitude into sunlight. And that region also hosts a jet that carries larger grains. If brine is erupting and freezing into beads, the two should travel together like cousins who share a playlist. A compromise proposal lands. Demand a trifecta. 1. The spectral humps align with salt analogs across multiple angles. 2. Polarization behaves like smooth, near-spherical beads during those same windows. 3. The phase curve of the feature tracks the jet's heartbeat rather than the global coma glow. If all three sing in harmony, the dust masquerade loses plausibility. No one is fully happy. That is how you know the plan is balanced. By dusk, the verdict is very likely salted, with a footnote the size of a novella. The phrase consistent with brine-derived aerosols earns a place in the draft. Table salt does not. We are not seasoning dinner, we are untangling light. Still, when the lights go off and screens power down, the corridor chatter has a new brightness. If these features truly come from droplets shattered and flash frozen as they raced through a crack, then the nucleus houses not just ice, but liquid that learned to carry a memory of rock. Next, we turn to the other character who keeps popping up in the spectra like an eager extra, the molecule that loosens winter's grip and changes what worlds can do when the thermostat says no. Chapter 6, Ammonia, Antifreeze of the Gods. Ammonia, antifreeze of the gods. Why ammonia screams ocean chemistry. It lowers freezing points, buffers pH, and plays nice with rock to make life's pantry less fussy. Also, ammonia is basically water's extrovert friend who gets the party started. Imagine an ocean determined to exist in a neighborhood that would rather it became a glacier. The thermostat reads no, the sunlight is stingy, and the ice shell overhead is the kind of thick that makes mountaineers sigh. Enter ammonia, clinking imaginary glasses and breezing past the bouncer. Where pure water would seize into crystal, water mixed with ammonia stays liquid at temperatures so low they should require a disclaimer. This is not a minor tweak. In the right proportions, ammonia drags the freezing point down by dozens of degrees, creating a secret lane where liquid can navigate under winter's nose. If water is the diligent worker, ammonia is the friend who says, "Trust me," and somehow the party does not end at midnight. This trick rests on the way ammonia and water disrupt each other's routines. Water loves to organize into tidy crystal lattices when it cools. Ammonia is that one guest who rearranges the furniture. It slots into the structure, breaks the rhythm, and makes it harder for water to snap into its usual grid. The result is a mixture that prefers flowing to freezing until the cold becomes truly heroic. For an icy world nursing a warm interior, this is golden. You do not have to keep everything tropical. You only need to keep pockets, channels, and reservoirs just warm enough. Ammonia extends that comfort zone like a thermal blanket sewn out of chemistry. But ammonia's resume is not just temperature shenanigans. It is also a referee in the eternal scuffle between acids and bases. Dissolved ammonia becomes ammonium, a form that happily mops up excess acidity. In a water rock environment where minerals donate and steal protons like over-caffeinated bankers, this buffering matters. It calms wild swings, creating a steadier chemical stage on which slow reactions can play out. Imagine a kitchen where the oven decides to spike and crash every 5 minutes. Baking anything complex would be a nightmare. Ammonia, by damping those swings, keeps the oven honest. That steadiness helps preserve dissolved carbon species, keeps metals from dropping out of solution too fast, and generally makes it easier for a liquid to remember it is a liquid with ambitions. Now picture that liquid meeting its first love, rock. When water alone flows through fractured silicates and iron-rich minerals, it picks up ions, changes its mood, and sometimes precipitates layers that clog the plumbing. Add ammonia and the negotiations change. Certain metals stay dissolved longer. Some reactions that would stall at low temperatures start to crawl forward. The mixture carries a broader palette of ingredients away from the interface, like a shopper with a bigger basket and a coupon for patience. Over long spans, this can build up distinctive inventories, more nitrogen-bearing species, altered ratios of dissolved carbon versus carbonate minerals, and a general vibe that says the system had time to think. Ammonia also loves to hitch rides with other volatiles. It can capture carbon dioxide into soluble forms and escort it through chilly conduits that would otherwise trap it as rock or frost. That means worlds rich in ammonia can shuffle carbon from deep stores to near-surface environments without needing a tropical heat wave. A quiet conveyor belt, powered by chemistry rather than sunshine, is the kind of thing that keeps a subsurface sea interesting even when the exterior looks like a frozen postcard. From a physical perspective, the mixture matters for motion. Liquids with ammonia are generally less viscous at the same chill than their pure water counterparts. Less goo, more go, that changes how easily fluids percolate through pores. how fast cracks refill, and whether a vent can pulse rather than clog. In the mechanics of tiny worlds, viscosity is destiny. If your ocean moves like syrup, you get one style of geology. If it moves like a well-chilled broth, you get another. Ammonia leans toward the latter, favoring circulation, convection at modest heat gradients, and channels that refuse to retire after their first performance. Thermal memory enters the story too. Mixtures with ammonia store and release heat differently, as they cross their freezing and thawing thresholds. When a fluid pockets under ice and begins to freeze, it releases heat, resisting the freeze for a while. When it melts again, it absorbs heat, smoothing the thaw. These hysteresis loops soften the harshness of day-night cycles, or episodic heating, letting reservoirs linger in a liquid-friendly limbo, longer than a pure system would. In practice, that can mean vents that remain viable late into local night or seasons, and subsurface conduits that do not collapse at the first sign of a chill. Chemically, the presence of ammonia leaves signatures that an attentive spectrum can sniff. Certain nitrogen-bearing compounds that form from or alongside ammonia have recognizable spectral quirks. When these appear in step with water features, and in environments that are otherwise too cold for pure water shenanigans, the case for ammonia strengthens. This is not the shouting kind of evidence. It is the self-assured wink. You do not see a neon sign that reads ammonia here. You see a pattern of behavior that only makes sense if ammonia has been whispering in the background. There is a biological footnote that refuses to stay in the margins. On Earth, ammonia feeds metabolisms and participates in building blocks when conditions are right. We are not smuggling Earth's playbook into an alien stadium, but we can appreciate a general rule, a solvent that stays liquid broader and longer, that ferries carbon chemistry with fewer tantrums, that keeps acidity in a friendly range, is a solvent that gives complexity more time. Time is the currency of chemistry. Ammonia prints small bills that spend easily in the cold. None of this requires oceans to be vast. Even networks of briny corridors can shape a world's character if they are persistent. That is the quiet magic of ammonia. It does not arrive with trumpets. It sits in the mixture, lowers the stakes for freezing, steadies the pH, and lets water and rock gossip for longer without flipping the table. The result is a chemistry that feels less hurried and more articulate, the kind that can write notes into vapor that we, from far away, can read. Next, we will follow that buffering role where it naturally leads into the ledger of acidity and alkalinity, and how a sea under ice leaves its pH signature in the light. Chapter 7, Phoning in on an Ocean. Phoning in on an ocean, pH, carbonates, and the balancing act between rock and water. We model a world where the core whispers ions into a long-lived sea, and show how that fingerprint rides the vapor like a message in a mist. Imagine a buried sea wearing an ice roof and a stone floor. The ceiling barely changes, but the basement never stops talking. Rock is a quiet conversationalist, yet over years, it leaks opinions into the water. A little calcium here, a nudge of magnesium there, a hush of dissolved carbon that can decide whether the liquid is sour or smooth. pH is the mood ring of that conversation, and carbonates are the notepad. Read them right, and you can tell who started the argument and who finally made peace. Start at the bottom, where cracks let water thread into the core. Every fracture is a kiosk where minerals trade ions for patience. Some reactions pull acidity out of solution, others contribute it. The overall tone depends on the mix of rock types, the pace of heating, and how long the water sticks around. If silicate minerals dominate, the water tends to lose acidity as it picks up metals. If the floor includes rock that feeds alkalinity, the liquid drifts toward a calmer, more buffered state. None of this requires high-temperature drama. Even lukewarm contact, sustained for ages, can tilt the balance. Chemistry is a marathon runner with very comfortable shoes. Now invite carbon into the room. It shows up dissolved as a family of cousins: carbonic acid, bicarbonate, And carbonate, which cousin dominates, depends on pH, like a vote that swings with the crowd. In more acidic settings, the weaker forms take charge. In more alkaline settings, the fully deprotonated, strongly buffering member steps forward. This family is a built-in shock absorber. When the environment tries to swing, the carbonates lean the other way, catching the punch. That buffering means a subsurface sea can shrug off local disturbances, say a sudden pulse of venting or a burst of fresh rock exposure, without flipping character. Modeling this balance is less about fancy equations and more about storytelling with guardrails. You set a starting composition for the rock, specify how energetic the interior is, and let the water wander through time. Each time step, the liquid visits the basement kiosks, exchanges ions according to the rules, and moves on. You keep track of how much carbon arrives from below or above, where it parks in minerals, and when it prefers to stay in solution. The output is a pH that evolves, not randomly, but along a path guided by the constant tug-of-war between dissolution and precipitation, between the urge to build mineral layers and the urge to carry them away. What does this have to do with a coma of gas and dust around an interstellar passerby? Everything, because a liquid's personality is surprisingly portable. When that sea vents through a crack, the bubbles and droplets do not just carry water, they carry the sea's history in the proportions of dissolved carbon species and in the subtle company they keep, traces of calcium, magnesium, sodium, and friends that ride along as salts or as the ghosts of future minerals. As droplets flash to vapor, the dissolved carbon shifts forms again, releasing gas or clinging to tiny aerosols. The exact split depends on pH back home. A more alkaline ocean favors certain salts that make aerosols more likely. A more acidic one bleeds more dissolved carbon into the gas phase. The plume, in other words, is handwriting done in mist. There is a second messenger, the way the gas itself carries balance. When pockets vent, they bring out mixtures of water vapor and dissolved carbon dioxide that was once tamed by bicarbonate. If the ocean was well buffered, the ratio of water to carbon gas in the plume tends to stay steady even when the vent pulses. If the ocean lacked buffering, that ratio sways with every thermal twitch. Watch the coma over a rotation, and you can see the difference. One traveler keeps its exhale on tempo. Another wheezes offbeat when a hot spot swings into sunlight. The tempo is pH, wearing a metronome. Minerals leave breadcrumbs too. Precipitation at the seafloor locks some carbon away as solid carbonates, which sets a ceiling on how much dissolved carbon the liquid can carry upstairs. If the basement has been actively building carbonate layers, the ocean arriving at the crack is relatively lean in carbon. If the basement has been stingy, the ocean is richer and more eager to vent carbon gas. Add in trace metals that co-precipitate, tiny amounts of strontium, a smidge of iron, and you get side notes that can nudge spectral features in or out of visibility. No need for the full periodic parade, just enough to tilt the optical scales. Of course, the path from vent to telescope is a gauntlet. Gases expand, cool, and sometimes condense. Droplets shatter into sprays that freeze into beads or platelets. This is where an ocean's pH leaves its most stubborn mark. In the aerosol's survival, more alkaline brines form particles that resist drying into jagged shards. They hold water a beat longer and scatter light with a smoother signature. Less alkaline brines crisp quickly, leaving sharper, more angular residue. The coma's polarization and phase curves, how light wiggles and brightens at different viewing angles, quietly respond. It is like reading a perfume by the trail it leaves on the staircase. What keeps the ocean's pH from wandering off over eons? A feedback loop with decent manners, too much acidity, and rock reactions accelerate to neutralize it. Too much alkalinity, and minerals form that pull the system back toward the middle. Add the occasional reset button, fresh fractures that expose new rock, minor tides that shuffle heat, and the sea settles into a band of acceptable moods. That stability pays dividends at the vent. Instead of chaotic chemistry that changes every week, the plume presents a recognizable house style. You can taste it in the ratios of carbon species, in the persistence of specific salt families, and in the way small temperature swings fail to knock the features around. In practice, we build ensembles of models and ask which house style best matches the music in the coma. The winner is not a single pH point, but a corridor, perhaps mildly alkaline, perhaps leaning toward neutral with a sturdy buffer. Within that corridor, the time variability of the coma makes sense. The aerosol behavior looks right, and the gas ratios keep time like a well-trained drummer. That corridor is the ocean's calling card, and once you have it, you can begin to speculate about the basement's layout, what minerals are common, how vigorously the interior warms, and how quickly the cracks cycle between open and clogged. And once you can read that mist-written card, you are ready to invite the smallest raconteur onto the stage. The heavy light balance in the water itself, a tiny isotopic tilt that remembers birthplace and childhood temperature. Our next chapter hands the microphone to that detective in the tiny hat. Chapter 8. Deuterium, the detective with a tiny hat. Deuterium, the detective with a tiny hat. Isotopes step onto the scene, heavier hydrogen and oxygen ratios that tell birthplace and temperature history. Our miniature detective tips us off. This water did not grow up around here. Imagine water molecules as travelers with luggage. Most carry the standard light hydrogen, but a small fraction lug around heavy hydrogen, which is hydrogen with an extra neutron tucked into its suitcase. That extra neutron is tiny on human scales and mighty on molecular ones. It changes how the molecule vibrates, how it bonds, and crucially, how it behaves when temperatures tumble. Heavy hydrogen turns a regular water molecule into a slightly slower dancer. In physics terms, the steps are the same. The rhythm is just more deliberate. Our detective wears a tiny hat because its clues are subtle and fashionable. Why does this matter? Because the cosmos is a grand sorting machine. In very cold environments, the chemistry that builds water leans toward the heavy version. Reactions favor the more stable, slower dancer when everything is chilled to the marrow. In warmer places, that advantage fades. Over time, the balance between heavy and light in water becomes a thermometer that remembers yesterday. Measure that balance in a plume or a coma, and you are not only tasting a world's liquid, you are reading the diary entries about the climate where that liquid was born or stored. The practical trick is spotting heavy marked molecules in the rainbow of light. They absorb and emit at slightly shifted colors because their vibrational steps are weight adjusted. On the spectrograph, those shifts are tiny nudges, barely a shoe size difference, yet they repeat with patient regularity. Stack enough photons, and the pattern emerges. Here a line for regular water, there a faint cousin for the heavy flavored version. The ratio between those lines, corrected for temperature and optical crowding, gives you the heavy to light proportion. It is celestial forensics. No fingerprints, but plenty of footprints. Now, water is not the only gossip. Oxygen has its own heavy variant as well. A water molecule with heavy oxygen behaves differently again, offering a second dial to turn. By comparing heavy hydrogen to heavy oxygen signals, you can separate effects caused by temperature from those caused by selective escape during venting or by sunlight nudging molecules apart. Think of it as using two clocks to tell whether your watch is slow or the day was long. When both clocks agree, you trust the hour. When they disagree, you know some mischief happened on the way out of the vent. Let us talk fractionation without making anyone nap. Fractionation is just the universe's habit of sorting species during phase changes. When liquid turns to vapor, lighter molecules escape first. When vapor condenses, heavier ones settle into the droplet with a bit more enthusiasm. Each step leaves a bias, a small tilt in the ratio. If you chain many steps together, freezing and thawing, venting and recondensing, you end up with a signature that encodes the sequence. That signature can say, I formed in the deep cold and was barely disturbed, or I was born modestly chilly and then put through a freeze dryer 3 times before brunch. Interstellar travelers complicate and clarify this all at once. Complicate because their surfaces have been sandblasted and baked by cosmic rays and distant starlight. Clarify because deep reservoirs can stay shielded for a very long time. A crack that taps into an ancient pocket will deliver water whose heavy-to-light balance still remembers the nursery where it condensed. If that nursery was a frigid cloud between stars, heavy hydrogen will be relatively abundant. If it was nearer a warm young star, the balance will lean lighter. Our little detective's hat begins to glow, but there is an even more specific clue: the mismatch between what we expect from local comets and what we measure in the newcomer. Local families of icy bodies often cluster around certain heavy-to-light ratios. A regional accent picked up during formation. When a visitor speaks with a different accent, when its heavy hydrogen ratio stubbornly refuses to match the local choir, we have a strong hint that it did not originate anywhere near our neighborhood workshop. The accent test is not perfect, but it is wonderfully nosy. Temperature history is only part of the story. Storage matters too. If a world kept its water locked in ice for ages, then occasionally melted it into brine and refroze it, the repeated phase changes would keep nudging the ratios in predictable direction. A brine that spent many cycles close to vents could end up slightly depleted in heavy hydrogen because the lighter molecules escape first and set the tone. A brine that lurked quietly under thick ice might preserve the original cold cloud signature more faithfully. When we see different vents on the same object exhale slightly different heavy-to-light balances, we are watching a photo album of reservoirs. This one outgoing, that one reclusive, the other a social butterfly with a history of near-surface drama. Measurement is an art of patience and subtraction. Telluric lines from our own air must be peeled away. Instrument quirks must be trained to sit. Rotational broadening, thermal smearing, and overlaps with faint organic lines must be coaxed into revealing their separate voices. When the collapse of uncertainty finally narrows, you are left with a ratio that is not just a number, but a story. In our case, the story leans toward a childhood in deeper cold than most local comets, combined with a life of intermittent venting that did not erase the original accent. The detective tugs the brim of the tiny hat. Case not closed, but the suspect description is clear. What about oxygen's heavier variant? It tends to be less excitable during phase changes than heavy hydrogen, so it acts as a reference frame. If heavy hydrogen is telling you about temperature and venting, heavy oxygen whispers about the primordial mixture from which the object was built. Together, they give a two-dimensional map, one axis for thermal past, one for ancestral recipe. Plot our visitor on that map, and it parks in a quadrant where local comets rarely camp. Not impossible, but distinctly unneighborly. The best part is how these isotopic clues triangulate with everything else without repeating it. Salts, ammonia, and pH tell you about the ocean's present personality and its dialogue with rock. Heavy to light ratios tell you where that ocean's water likely came from and how it was treated on the road to the vent. One speaks about cuisine, the other reveals the passport and travel history. Put them together, and the picture goes from postcard to panorama. Next, we will leave the vapor for the solids and open the cabinet of minerals that freeze mid-story. These are the salts that remember crystals that trap a timeline inside their lattice and refuse to forget. Chapter 9. Salts that remember. Salts that remember chlorides, sulfates, and unexpected companions that crystallize stories from freezing brines. Each mineral is a diary entry. We just need to translate the handwriting without smudging the page. Picture a droplet launched from a crack, tumbling into cold, so sharp it bites. It starts as a tiny world of liquid order, water holding hands with ions, a pocket parliament arguing over who stays dissolved and who is voted out as a crystal. As the chill tightens, the group breaks up according to rules older than starlight. Chlorides step forward first in many mixes, claiming the earliest benches as neat cubes or ragged plates. Sulfates arrive later, sometimes flamboyant, sometimes modest, decorating the edges like late guests who still steal the scene. What precipitates, and in what sequence, is not random. It is choreography guided by concentration, cooling rate, and the company of trace characters that crash the party at the last minute. Frozen brine is not just solid water. It is a cabinet of microfossils from a liquid conversation. Crystals keep minutes in their shapes. Cubes with right angles whisper that the environment did not rush. There was time and space for faces to grow evenly. Dendrites, those fern-like sprays, tell of supercooled moments when molecules piled on faster than they could arrange themselves, like scaffolding thrown up the day before an inspection. Needles and whiskers, thin as hair, hint at a directional push of temperature or a pressure gradient nudging growth along a favorite axis. When we find these habits locked inside fragile grains, we are looking at snapshots of the cooling path, the timeline etched as geometry. Hydration layers add another chapter. Many of these salts carry water in their structure, not as trapped puddles, but as a formal part of the lattice. That captured water is a thermometer with memory. Lose a little, and the crystal changes phase, shifting its angles and optical attitude. Gain a little, and it swells into a more open framework. Cycling between these states leaves strain lines, microfractures, and zones of slightly different composition, like tree rings in miniature. Under a microscope, you would see ghosts of old winters and brief thaws. In scattered light from a coma, those transitions soften or sharpen features in ways that betray how often the droplet flirted with melting before surrendering to ice. Impurities are the marginalia. A pinch of iron traces, a smudge of magnesium, a dash of calcium can be invisibly small, yet completely decisive. They tweak solubilities, push one mineral to appear before another, and alter the color and texture in ways our instruments can sniff. Co-precipitation is the backstage deal here. An ion that would otherwise sit patiently in solution gets dragged into the lattice of a more enthusiastic neighbor. The result is a crystal wearing a borrowed element, a disguise that records who was present even when that guest did not earn their own mineral. Later, when that grain warms and redissolves, the stowaway can slip back into the liquid and bias the next round of growth. Memory is not a single event. It is a loop. Layering is where the diary gets juicy. As a vent pulses, concentration surges and retreats. Crystals accrete in thin coats, each coat reflecting the brine's mood at that moment. Under slow cooling, bands are broad and orderly, the geological equivalent of neat handwriting. Under spasmodic venting, bands are thin and erratic, like notes scrawled in a moving bus. If a later pulse arrives richer in sulfate, a pale rim might wrap a darker chloride core. If the reverse happens, clear cubes could wear delicate halos of feathery sulfate. These juxtapositions are receipts. Receipts we can sometimes read through how the particles scatter light as they tumble. Texture matters for survival. Smooth beads shed light in a different pattern than jagged shards. Aggregates, little clumps of many crystals sintered together, act like fluffy snowballs that are more likely to ride the gas and less likely to fall back. A glassy skin can form when a droplet flash freezes, sealing in a slush of microcrystals that continue to grow at a crawl. Crack that skin later through thermal stress, and a confetti of fines explodes outward, tweaking the coma's brightness while leaving the bulk composition unchanged. The timing of those crack events imprints faint, repeatable rhythms on the dust flow. Rhythms that align with spin and sunlight, but can only be explained if the grains are not just rock powder, but memory foam for chemistry. There are plot twists. Some salts that ought to be wallflowers in gentle conditions become extroverts when the brine is crowded. At high concentration, lesser-known companions crystallize as complex hydrates with labyrinthine structures. These lattices trap pockets of leftover brine like tiny terrariums. Each pocket is a sealed proverb from the moment of solidification. When the grain later warms, those inclusions can burst or bleed, changing the surrounding texture and spiking the local vapor with a flavor that does not match the bulk grain. From afar, that shows up as quick glints of an unusual spectral note that wink and vanish like stage lights. Gravity, tiny though it is on a small body, draws another chapter in slow motion. Heavier grains settle back toward the vent mouth between pulses, where later eruptions can recycle them into the flow. Lighter, fluffier aggregates sail farther and seed the coma with a persistent background. The recycled heavy grains get annealed by repeated passages of warm gas, smoothing edges, healing microscopic wounds, and sometimes growing new overcoats from fresh condensate. The long flyers remain as they were, fragile, angular, more honest to the initial freeze. Two populations, two biographies, one plume, even fracture patterns speak. A crystal that snapped along clean planes indicates coherent, well-grown domains with little internal strain. A crystal that shattered into chaos reveals a history of stops and starts, of hydration jitters, of hidden defects seeded by trace elements stealing lattice seats they did not pay for. Those differences are not academic. They decide how much surface area the grain offers to sunlight, how fast it warms, how quickly it gives back its imprisoned volatiles, and whether it charges up electrically under radiation in a way that makes it dance to the local fields. Why does any of this matter for the larger mystery? Because these mineral diaries translate the timeline of a hidden sea. Sequence tells us whether the brine concentrated slowly or was splashed into supersaturation by sudden pressure drops. Habits sketch the cooling rate at the vent and the architecture of the underground plumbing. Hydration states whisper about the frequency of thaw cycles. Inclusions point to moments when the system was crowded with solutes, perhaps after weeks of evaporation under an ice ceiling. Put those pages together, and you infer not only composition, but cadence, the living rhythm of a liquid under ice. The challenge is reading without smudging, extracting signals from light scattered by grains that refuse to sit still. But the payoff is a story with characters and beats, not just a list of ingredients. Chlorides are often the opening act. Sulfates arrive for the chorus, and trace actors drop witty lines that steal the scene. It is mineral theater, and every curtain call is a clue. Next, we step back into motion, watching how vents switch on and off across a spinning body, and how chemistry swings with the spotlight, jet by jet, breath by breath. Chapter 10, Jet Lag. Jet lag time variable outgassing shows rotating vents and layered interiors. The light curve dances, the chemistry swings. Some vents cough organics, others exhale brine. 3I/Atlas is doing interpretive dance. We are the confused critics, taking notes. First comes the flicker. Night after night, the brightness rises and falls with a rhythm that is not the orbit and not our atmosphere doing a practical joke. It is the object turning, exposing fresh plumbing to sunlight, then tucking it away again, like a shy performer who only sings on the chorus. We stack the measurements into a light curve, a wobbly heartbeat that reveals the spin. Finding the period feels like learning a drum pattern from a neighbor through the wall. You catch the main beat, then the offbeat, then the little flourish that only appears when the kettle really boils. Once the rhythm is in hand, we begin the duet. Brightness in one ear, chemistry in the other. We take spectra along the spin, slicing the coma into timestamps. Some phases bring a gentle blue slope and a neat set of water features. Other phases arrive with extra warmth in the red and a shy forest of organic signatures that only step forward when coaxed by patience. There are moments when salts speak up. moments when they keep their dignity, and rare interludes when both factions share the stage like rivals forced into a duet at karaoke night. The pattern repeats with rotation, but never identically. Vents are living things, and living things improvise. Different vents clearly own different moods. One sector of the spin favors organics, broad fluorescence, the soft glow of larger carbon chains airing their laundry. Another sector leans briny, smoother aerosols, polarization that behaves like tiny beads rather than rough dust, and those gentle infrared humps that lab analogs taught us to respect. The timing of these peaks is offset from the raw brightness because gas and dust do not accelerate equally. A warm patch lights up fast. Chemistry needs a minute to move through the plumbing. The result is a phase lag, a small but telling delay that says the vent is not scraping the surface but drawing from somewhere deeper. That delay is our first clue about layering. Imagine stacked reservoirs under the ice, a shallow pocket that answers the phone immediately, and a deeper one that lets it ring twice. When dawn hits, the shallow pocket puffs out quickly with lighter gases. By the time the area rotates toward late morning, the deeper pocket has warmed enough to join the call, pushing brine-rich sprays up the same fracture or one next door. On the light curve, you see a two-step, a quick rise tied to the shallow exhale, then a second, chemically distinct bump a few ticks later. It is not a random duet. It is a stairwell echo between floors. Dust adds syncopation. Coarser grains take longer to launch and longer to leave the neighborhood. So a vent that produces chunky stuff leaves a brightness tail that lingers beyond sunset, while the gas features fade promptly. Compare that to a vent flinging mostly fine spray, and you see the opposite. Chemistry spikes and relaxes, while brightness barely notices. Map these behaviors across the spin, and you get a quilt of personalities. One quadrant is a sprinter with light feet. Another is a powerlifter who keeps dropping chalk on the floor. The spin itself is not perfectly behaved. Small, steady pushes from jets act like 1,000 tiny hands nudging a merry-go-round. Over a week, the period drifts by a breath, and the phase of the chemistry peaks slides unless you account for it. We update the timing model and watch the peaks snap back into place, which is both satisfying and unnerving. The traveler is steering itself with its own breath, like a canoeist who insists on paddling only on the left. Aliasing tries to crash the party. Our observations are chopped by daylight and weather, so a false echo can masquerade as a second period. We defeat the imposter by comparing chemistry and brightness together. A fake period might trick the brightness alone, but it will not line up with both the salt humps and the organic glow across multiple nights. When all three agree, light, salt, organics, you can plant your flag. The spin is real, the offsets are real, and your coffee is finally justified. There is drama between vents too. On one rotation, the brine sector underperforms while the organic sector goes for a victory lap. On another, the situation flips. We suspect plumbing politics. Fractures share pressure. When one conduit draws hard, it steals a bit from its neighbor, the way one straw in a milkshake bullies the other. Over several rotations, you see anti-correlations as if the vents are negotiating union rules in real time. The interior is not a single tank. It is a network of straws, pockets and valves that prefer fairness only on alternate Thursdays. Thermal inertia writes the evening act. A patch that has been sunny for hours stays warm after sunset, like a brick wall radiating into twilight. Those vents keep talking longer, and their chemistry peaks drift into the dark in a way morning vents never do. That asymmetry tells us about material properties, grain sizes in the skin, porosity, and how tightly ice and dust are knit. It also limits how deep the heat wave penetrates each day. The phase lag between light and chemistry gives you a ruler for the thermal skin depth, without drilling an impolite hole. Now for the showstopper, sporadic flares that ignore the schedule. A vent clogs, pressure builds, and then a brief, rude burst resets the decor. These flares carry bigger chunks, spike the brightness, and temporarily flatten spectral features by burying the signal in a snowstorm of light scattering. 10 minutes later, the tantrum is over and the regular rhythm resumes, now with a slightly altered baseline. Catalog enough flares, and you see preferences. The brine sector flares when the rotation brings maximum stress across a particular crack. The organic sector flares when the local slope faces the sun at a low angle, hinting at surface creep that pinches the mouth. The object is not falling apart, it is clearing its throat. In the midst of all this choreography, the most delightful plot point is the way colors swing with purpose. The coma grows redder when organics dominate, bluer when salty beads take the stage, and neutral when dust alone plays filler. The swings are small but consistent, so small you would miss them without the period in hand, and so consistent you cannot unsee them once you do. That color metronome lets smaller telescopes join the dance, confirming the phase with simple filters while the big instruments pass the chemicals. It becomes a community effort. One team marks the beats, another writes the lyrics. By the end of the campaign, we have a rotation map that is less a picture and more a score. Measures marked organics solo, bars labeled brine duet, rests that mean everyone breathe. It is impossible to unhear the structure once you have heard it. The interpretive dance is not random. It is a layered interior answering sunlight in tears, a secret architecture sketched in time instead of stone. Our notebooks read like reviews from baffled but charmed critics. Bold choices, confident timing, occasional confetti. Next, we will step behind the curtain and ask how such seas are forged in the first place. What engines warm an icy world long enough to brew chemistry with opinions and keep the orchestra tuning beneath the ice? Chapter 11. The Ocean Makers. The Ocean Makers. How rocky cores, tidal flexing, and radiogenic heating forge seas beneath ice. We compare a menu of alien worlds, big, small, dimly lit, but all capable of brewing the same salty broth. Start with a stone wrapped in frost. Give it a quiet heart that never quite cools, a shell that traps warmth, and a few good excuses to knead itself from the inside. Leave it in the dark and come back later. Against common sense, you will not find a solid statue. You will find pockets and layers of liquid, moving like thoughts behind a calm face. The universe is full of introverts with rich inner lives. 3 kitchen appliances build these hidden seas. First is the slow cooker in the core, radiogenic heat. Even tiny amounts of heat, spread over ages, keep rock from going fully numb. Minerals relax, pores widen, and ice perched above starts to feel a faint warmth rising like steam through floorboards. It is not dramatic. It is camping stove energy across geologic time, which is exactly how you simmer a broth without burning it. Because the heat comes from within, the system is less moody than anything powered by fickle sunlight. Day and night may play on the roof, the basement keeps humming. Second is the kneading machine, tides. Put your world on a slightly misshapen path around a giant, or lock it into a rhythm with a few unruly neighbors, and gravity will flex it on every lap. Rock is stubborn until you massage it for long enough, then it turns that flex into heat. Cracks open and close, friction sighs into warmth, and any water trapped in the plumbing begins to move. Tidal heating is the cosmic equivalent of doing squats forever. You may not love the workout, but you cannot deny the temperature. The most effective setups are messy. Give the world a mild orbital wobble, a partner in resonance, or a tilt that refuses to settle, and the tides keep changing enough to avoid boredom. Bored tides cool, fickle tides cook. Third is the lid, insulation. Ice, especially when it is layered with dust, is a terrific blanket. It blocks radiation to space and slows conduction to a crawl. A world with even a modest heat source can hoard that warmth. If the shell is thick and a little crumbly, full of trapped bubbles and fractures that break the march of heat outward. The lid does not need to be perfect. It just needs to be patient. Place a blanket over a pot on low heat, and you can keep soup warm long after the stove is switched off. Same idea, larger kitchen. Now build the menu of possible worlds. Large, distant worlds, big enough to hold heat like a thermos, far from their star, so surface ice never melts and runs away. Their interiors differentiate into layers. The denser stuff sinks, the lighter stuff floats, and in that stacking, the rocky middle keeps warm. Here, the oceans can be grand, sandwiched between a thick crust and a deep rock floor. The seas last because the heat reservoir is huge and the shell is heavy. If they have a patient giant for a neighbor, tides add spice. Big worlds love a slow simmer. Medium worlds with fussy orbits. Think small moons or minor planets that dance in step with larger bodies. Their own gravity is modest, so they radiate heat to space faster, but tides keep turning the crank. They get patchwork oceans, regional seas, long corridors of liquid, aquifers that merge and separate like a city's water system under construction. These worlds are drama queens in the best way. Their interiors are rarely uniform, which means the seas can migrate, expand, and shrink as the plumbing evolves. You do not get one ocean, you get a touring schedule. Small, stubborn worlds, the ones that should be frozen through if the universe played by simple rules. They survive on thrift. Radiogenic heat trickles. The lid is extra stingy with leakage. The core is porous enough to host slow reactions that release a little extra warmth. On these worlds, seas are more like networks of briny veins than grand basins. They matter because they can be surprisingly long-lived. Thin liquids move more easily through tight spaces, and small worlds can flip between freeze and flow without cracking themselves apart. Think of them as pocket oceans, the espresso shots of planetary hydrology. In each case, the ocean is not an isolated lake. It is a negotiator between rock and sky. Water seeps into fractures, meets minerals, extracts flavors, and returns altered. That movement is powered by tiny imbalances. A slight difference in pressure here, a temperature gradient there, tides that tug and loosen like a very slow breath. Where heat funnels upward, convection cells roll. Slow, persistent churning that ferries warmth and chemicals across great distances. Where the shell thins above a warm plume, the roof may sag a little, forming a lens where liquid gathers, restless against its ceiling. Over time, the interior builds a personality. Places that tend to vent, places that never do, thoroughfares where brine prefers to travel. We should talk plumbing. The best oceans are connected to their rocks by real pipes, not crushed talc. Fractures must be open, or at least willing to reopen, when tides pry. This is where the mechanics of a world's crust matter. A brittle lid can crack and seal in cycles, providing valves that pulse. A more ductile lid slumps, using slow creep to keep channels from pinching shut. Both styles can support a long-running system. The former gives you episodic fireworks. The latter gives you steadier founts. Either way, the sea endures because it can breathe. Saltiness is not an accident. It is a survival tactic. As water circulates through rock, it borrows ions that lower its freezing point and improve its willingness to flow at polite temperatures. That brine also increases density, allowing the liquid to hug the rock floor while fresher melt. When it appears, floats above. Layering follows, not as a single sheet, but as a stack of moods, dense and seasoned below, lighter and newer above. If a crack taps the lower layer, you get a confident, mineral-rich outburst. If it skims the top, you get a cleaner whisper. The ocean beneath is a tiered cake. Vents slice different layers depending on their depth. All of this can happen in the shadows. A world does not need generous starlight to make and keep a sea. It only needs energy sources that do not care about day, a lid that mines the store, and time enough to do the slow work. Across the menu, from giants' moons to lonely wanderers, Those conditions crop up in combination more often than our imagination used to allow. The recipe is flexible: increase tides, decrease radiogenic heat, thicken the lid, cut back on size, tilt the orbit, stir the convection. Many kitchens, same soup, and once a hidden sea exists, it starts writing postcards. Vents telegraph pressure changes, salts crystallize into diaries. Isotopes keep score of birthplace. The surface looks quiet, but the light carries all the noise from below. If anything, the variety of ocean makers suggests a deeper truth. The universe does not favor one path to liquid. It likes options. It is a choose-your-own-adventure book with a wet ending. Next, we will let those liquids meet carbon chemistry at the vent mouth and ask a question that makes grant committees sit straighter. When organics brush past brine in low sunlight, what kind of chemistry gets a head start? Life's favorite soup to go. Chapter 12. Life's favorite soup to go. Life's favorite soup to go organics meet brines at the plume interface. We explore amino-lean hints and carbon backbones without over-promising, like a trailer that teases life without spoiling the plot. Picture the vent mouth as a street food stall at absolute zero's temperate cousin. On one side, brine rushes upward, seasoned by rock and steadied by that friendly antifreeze personality. On the other side, a thin halo of gas and dust waits like hungry customers. The moment the brine bursts into lower pressure, it flashes into spray. Droplets hang for a heartbeat, then freeze, then crack, then keep going as tiny spheres and jagged flakes. In this brief, chaotic corridor, organics ride the updraft, small rings, short chains, and a confetti of carbon pieces cooked in the basement, skimmed from rock, or stitched on surfaces deeper down. The stall is open for seconds. Chemistry lines up anyway. Interfaces are where the drama hides. A droplet that was liquid one blink ago still has a skin of mobile molecules. Organics bump into that skin and stick for a moment, sorting themselves by shape and attitude. Polar species choose to loiter near the brine, like party guests who want to be close to the snacks. Greasier chains hover just outside, flirting with the surface and then peeling away. As the droplet freezes, the surface squeezes them into ridges and pockets, trapping small collections that would never meet in a calmer setting. It is speed dating, but for molecules, and the host has a stopwatch. Sunlight, weak though it may be out here, arrives like a gentle coach with a whistle. A photon tagged from the bluer end nudges an organic into an excited pose. Another photon lands, and bonds rearrange. No fireworks, just a steady push toward larger frameworks, or toward tidier fragments, depending on who is sitting next to whom. Minerals in the droplet are not passive. Sulfate patches behave like tiny hawkers, offering reactive sites where a carbon chain can latch and grow a side branch. Chloride bands are more aloof, encouraging rearrangement. Only when the surface is crowded. The frozen skin becomes a mosaic of microreactors, each square a slightly different recipe card. Trace oxidants and gentle radicals, born from sunlight, nibbling at water, and from charged grains doing slow mischief. Add seasoning. They tip a chain here, open a ring there, create a handle that lets a fragment dock with a neighbor. If you were designing a prebiotic workshop in a clean lab, you would never choose this chaos. But the universe likes pop-up kitchens. Short lifetimes force fast deals. You do not build proteins in this breeze. You sketch carbon skeletons and hand them to the next station. The next station is aggregation. As grains and beads jostle, they acquire coats of frost and organic varnish. When two coated particles kiss, the varnish softens just enough to weld them into a larger, fluffier clump. Inside that clump, tiny voids hold pockets of trapped gas and a pinch of unfrozen brine, protected by the insulating embrace of the aggregate. These micronests can stay warmer than the outside by a laughably small amount. But on molecular scales, that is the difference between locked and limber. For a few extra seconds, reactions continue. You can almost hear the chemistry mutter. Do not tell the cold we are still working. Not all organic hints are equal. Some signatures whisper of aldehydes and acids, the darlings of early-stage carbon tinkering. Others hum with the faint chorus of nitriles and amines, which suggests that nitrogen found a seat at the table. We do not claim amino acids. The distance between amine-bearing fragments and tidy amino acids is a saga with many cliffhangers. What we can say is that the plume interface hosts the right kinds of rehearsals: carbon backbones with room to accessorize, side groups that like to shake hands, and a recurring rhythm of wet, freeze, thaw, shine, repeat. The choreography favors cycles. A grain launched today may settle back tomorrow and slide toward a warm crack, picking up heat before rejoining the spray. Each pass adds edits: a little more oxygen here, a longer chain there, a rearranged ring that is better behaved under light. Over dozens of trips, the grain becomes a scrapbook of interactions, a layered testimony of almosts. The point is not perfection, it is persistence. Chemistry grows into itself by trying again. Electrical fields near the vent add a small, mischievous push. Charged grains drift apart or together in selective ways, sorting assemblies by size, and coating. This segregation can create local habitats where a particular reaction dominates, the way a market alley ends up with 3 bakeries by accident and then becomes Bread Street forever. In one region, the grains lean toward orange, evidence of complex organics stacking layers like lacquer. In another, the grains run glassy, as if the brine won every argument and left little room for carbon drama. Even color gradients in the coma, faint as blush, become maps to these micro-neighborhoods. Could any of this cross the divide from interesting carbon to biological whispers? That is the question, with a velvet rope. The plume interface is fantastic at assembling backbones and adding simple decorations. It is less fantastic at building long, precise chains that fold into personalities. For that, you usually want repeated wetness without violent freeze, surfaces that hold and release with discipline, and time measured in patient afternoons. Still, the plume does one thing brilliantly. It packages complexity into aerosols and aggregates that can ride the wind and fall back in drifts. Those drifts can carpet near vent mouths, where warmth and moisture linger longer. There, beneath a thin snow of carbon confetti, slower kitchens can take over. The takeaway is not life here now. It is ingredients pre-mixed, batteries included. The most telling metric is evolution with rotation. When a brine forward vent and an organic forward vent share a neighborhood, the overlap period becomes a laboratory. Spectra taken during those minutes show subtle new features that are absent when either vent acts alone. They do not shout. They hint, a small shoulder on a band, a mild shift suggesting longer chains. It is the difference between a melody played on one instrument and the same melody enriched by a second. 2 stalls open at once, and suddenly the street smells like a plan. We also watch for resilience. Do these features survive after a flare, when larger chunks blast through and reset the local weather? If they do, then the process is robust, restarting quickly like a food truck that can serve in a storm. If they disappear for hours, then the chemistry is brittle, impressive only during calm. In our notes, the plume chemistry looks stubborn. It pauses, dusts itself off, and resumes. The kitchen has backup burners. None of this obliges grand announcements. The right posture is curiosity with a seatbelt. The plume interface is a crossroads where rock-flavored brine and carbon wanderers swap business cards. That exchange populates the near surface with starter kits. Somewhere under an insulating drift, maybe on a ledge warmed by a lazy vent, the kits might open, mix, and try more complicated dances. We do not know yet, but we know the caterer is generous, and the menu grows bolder with every rotation. Next, we duck back indoors to the one battlefield we can control, the clean room, where data pipelines glare, calibration frames posture, and chaos somehow learns to color inside the lines. Chapter 13, Chaos in the Clean Room. Chaos in the clean room, sample-free but data-rich, pipeline battles, calibration drama, and a whiteboard covered in equations that look like ancient runes. The punchline: even chaos can be reproducible if you label your axes. The door sighs shut, and the outside world vanishes into the muffled hum of air handlers and the faint squeak of sticky floor mats, doing their noble shoe deglittering duty. Hair nets, glove snaps, the ritual hand wiggle while nitrile settles into place. We are not touching stardust or bringing home pebbles from a distant shore. Our relics are photons, already captured, now imprisoned in files that behave like moody houseplants. Overwater them, and they sulk. Ignore them, and they die. The clean room's real contaminant is not dust. It is assumption. All pipelines begin as bright ideas with sharp elbows. Step 1. Pry the raw frames apart. For every exposure that looks like a picture, there are dark frames that record the camera's own murmur and flat fields that iron out the instrument's uneven attention span. Subtract, divide, and suddenly the cosmos looks less like a smudged painting and more like a ledger. The first time you run this dance, it is intoxicating. The 10th time, you learn that calibration is a pet you must feed daily, or it will bite. Bias drift, gain wobble, a pixel that decided to retire without notice. Everyone has a personality. We map them, corral them, and teach the software to stop taking their tantrums personally. A senior engineer calls this stage diplomacy. I call it therapy for detectors. The result is not perfection, but predictability. A predictable flaw is a friend. It shows up for meetings and brings its own coffee mug. Next, we face the whiteboard, which today resembles an ancient tablet from a civilization that worshipped Greek letters and subscripts. No symbols migrate into the final script, but in here they run wild. We wrap our minds around line profiles, instrument responses, timestamps that need to agree like synchronized swimmers. Photons fell on the sensor in a very specific order. Our job is to unshuffle that order without adding our fingerprints. Every board sketch, every box and arrow is an oath that we will not invent clarity where there was only fog. We build 2 pipelines on purpose and make them compete like reality television contestants with better hygiene. One is cautious, afraid of losing any whisper. The other is bold, ready to pounce on faint patterns. They agree often, argue sometimes, and when they disagree, we follow the argument back to the step where good intentions tripped over cleverness. Redundancy is not waste. Redundancy is faith with evidence. Then there is the calibration drama. Standard stars that are supposed to be boring are actually little divas. On some nights, they hum with unnoticed quirks that, if uncorrected, paint fashionable streaks across everything else. We do a ritual called the sanity loop. We reduce the standards 3 different ways and expect the same answer within agreed boundaries. If a method cheats, the loop catches it like a security camera that never blinks. Minimize pride, maximize loop. Time is a character, too. The object spins, the atmosphere breathes, and the instrument stretches like a cat after a nap. We anchor our clocks to a single, jealous timeline. Every frame gets a timestamp that can survive a storm. Without that anchor, phase curves smear, correlations dissolve, and patterns become pareidolia in lab coats. In response, we built a timing gate that checks each timestamp against 2 independent references, the way a bouncer checks both the face and the hologram on the card. If either frowns, the frame waits in the penalty box. Noise is not the enemy, uncharacterized noise is. We measure it, model it, and make friends with its statistics. Sometimes we even add noise on purpose, a tiny sprinkle to avoid the illusion that a perfectly smooth spectrum must be true. The universe is not smooth. If your graph is, you have filed it too aggressively. Meanwhile, we train the pipeline to avoid sharpening bumps into mountain ranges. Overfitting is science's version of contouring gone wrong. Peer review begins early in rooms like this. We blind ourselves to the result by scrambling labels, then ask, can you recover the known signals when you do not know which frames hold them? It is hide and seek with spreadsheets, and it keeps us honest. The point is not to win. The point is to avoid convincing ourselves that the shape we expected is the shape we found, because expecting is easier than finding. The best arguments are about axes. Label them, scale them, and choose units with mercy. Change the range by a hair, and a feature disappears. Change the baseline method, and the whole trend flips its mood. We hold a little courtroom where plots testify under oath. Why did you choose that smoothing window? Who authorized that mask around the suspicious region? Could a different binning turn triumph into shrug? No plot leaves without a provenance note that could be read by a stranger who thinks we drink our tea wrong. Reproducibility is where chaos becomes a house cat. Everything in the folder gets a readme that a time traveler could understand. We record software versions like passport stamps, bundle dependency lists, and freeze parameter files the way you freeze bread before a holiday. Later, when someone, maybe us, tries to replay the magic, the pipeline behaves. This is the moment when science feels like alchemy in reverse. You turn personal ritual into public recipe. And yes, we argue about color maps. High drama ensues. Some palettes flatter noise. Some conceal subtle steps. We pick ones that tell the truth, even when the truth is dull. Dull is fine. Misleading is not. The session ends when the same plot printed on 2 different office printers looks the same. That is not trivial. That is incremental heroism. At the end of the day, the clean room looks the same as it did in the morning. Soft lights, whispering filters, a whiteboard that could summon rain. But the files have changed. They are now a story we can read twice and still get the same ending. The chaos did not vanish. It learned choreography. Label your axes, and the universe will meet you halfway. Next, we turn the camera outward again, swapping sterile air for wild orbits, and ask a braver question. Where did our visitor come from? And what kind of world throws an ocean into exile without losing its taste for salt? Chapter 14, The Exiled Ocean Hypothesis. The Exiled Ocean Hypothesis. Narrative stakes rise. Perhaps 3I/Atlas was ejected from a system with multiple icy moons, or a super-Earth SeaWorld that lost its star's patience. Oceans can be homeless. Chemistry keeps their passport. Imagine a planetary system at dusk, not our dusk, but someone else's. 3 giant planets, pacing like bouncers, a ring of smaller worlds milling around the bar, and far out, a lantern glow where ice rules and tides rehearse their slow music. In that outer neighborhood, oceans do not sparkle under sun. They brood under ice, steady and private. Now add a little unrest. A migrating giant shoulders through the crowd. Resonances tug and release like a faulty elevator. Somewhere in that shuffle, an ocean gets its eviction notice. The body that carried it. Moon, dwarf planet, even a small oceanic super-Earth, finds a new trajectory that does not include home. The mechanics of exile begin with impatience. Planetary building is messy, and gravity is a loud negotiator. Put a giant planet on a slightly different path, and it starts stepping on toes. Small bodies gather in resonant chains around it, tugging at the same beats, exchanging momentum like gossip. If a resonance breaks during a close approach, one little world can catch a slingshot kick that turns a safe long loop into a door out of town. The escape route is not glamorous. It is a series of near misses that add up to a goodbye wave. Ejections from moon systems are even more personal. Picture a miniature solar system around a swollen planet. Inner moons warmed by tides, outer ones colder and quieter. As the giant's orbit around its star shifts, the tidal budget inside that moon retunes. A resonance between 2 siblings can intensify or fade. When it fades, the pumped heat dwindles. When it intensifies, the flexing grows. Either way, orbits drift. A moon nudged outward may wander into the domain of a chaotic three-body dance with a neighbor and the giant. In that dance, one partner gets a farewell shove. The giant does not cry. It barely notices. Gravity is generous with memories and stingy with empathy. Then there are the stellar drive-bys, the rare but devastating uninvited guests. A passing star brushes the outer system and rattles the marbles. Most roll back into place after a few million years of muttering. One or two, unfortunately aligned, do not. A small ocean world is tipped into a path that threads between the giants, and, after a season of terrifying cameos, it leaves with a velocity it cannot afford to repay. Exile achieved, court adjourned. What happens to the ocean during this bureaucratic disaster? If the world was small with a stiff lid and patient warmth below, it keeps its sea for a surprisingly long time. The ice crust thickens, vents dim, and the interior heat budget rebalances like a household moving to a colder city and switching to sweaters. If the world was larger and loaded with volatiles, its outer layers may puff and bleed for a while before the new cold clamps down. Either way, chemistry is the stowaway that survives the trip. Salt ratios locked into brine pockets, nitrogen-rich additives patiently buffering the liquid, trace metals remembered in precipitated layers. You can freeze the messenger, but the message persists. Now entertain a wilder origin, an oceanic super-Earth cut loose, not a hot sub-Neptune shedding an atmosphere in dramatic fashion, but a cool, deep-water planet that formed beyond its star's snow line and hoarded layers of liquid beneath a crush of ice and high-pressure ices. In a period of crowded migration, the star's inner architecture rearranged, and our sea world found itself pinballed outward. At some later point, a collision shaved off a sliver, still large by comet standards, rich in ocean material, and hardened by the long cold. That splinter became a vagabond, with a core's worth of minerals and a pantry's worth of salts. When such a shard warms near a new sun, it whispers of its parent in the only language it remembers, the chemistry of depth and pressure. Heavy, deliberate, seasoned. There is also the remnant hypothesis. Think planetesimal nursery, thick with half-built worlds that share a reservoir of icy debris. A pair of mid-sized protoplanets graze. One ends up with a temporary swarm of fragments, among them a compact object that once lived as the briny heart of a larger piece. The swarm clears, but the compact one remains, a seed of ocean memory now wrapped in its own crust. A later gravitational fistfight ejects it. The origin story reads less like a single tragedy and more like a sitcom where everything breaks in slow motion and the laugh track is tidal. The forensic puzzle is deciding which exile fits the accent we hear. Does the chemistry look like the broth of a tidally kneaded moon, heavy on certain salts that love recurring heat? Or does it tilt toward the deeper palate of a high-pressure ocean, enriched in species that form when water presses rock under layers of more water? Is the isotopic accent the kind you find in cold cloud formation that lingered in a gentle nursery, or does it hint at material processed in a busy circumstellar disk with plenty of ultraviolet drama? The answer is likely a blend, but blends still tell you which bottle dominated the pour. This is where the passport metaphor earns its page. Oceans stamp their travelers. A moon system built far from the star, sustained by tides, teaches brines to favor antifreeze mixes and buffers tuned for long, slow venting. A super-Earth sea world, deep and pressurized, cultivates a different balance, one that resists phase changes and stuffs more carbon species into solution before they consider precipitating. A nursery of planetesimals leaves lighter touches, a tendency towards simpler salts and fewer deep pressure signatures. Our visitors' papers do not list a home address, but they list favorite foods and old jobs. That is almost as good. There is a temptation to make exile sound heroic, a small world breaking free of tyranny to roam the dark in romantic solitude. Mostly, it is bookkeeping. Energy and momentum add, subtract, and what is left over becomes trajectory. Still, in the outcome is a kind of cosmic poetry. A sea that once listened to a particular star now hears another's faint warmth and responds like a seasoned traveler ordering coffee in a new language. The ice roof is a passport wallet. The vent is a customs window. The coma is the stamp. We will not know which origin story plays lead until we test the ways a sea can be stripped, punted, or tempted into the void, and what each route imprints on the cargo. So next we draft a short list of the universe's favorite eviction methods and ask how each one leaves a chemical fingerprint you can spot from a single pass of sunlight. 3 ways to lose a sea, with receipts. Chapter 15, 3 ways to lose a sea. Let us line up 3 disaster movies and watch the post-credits chemistry. Same protagonist, an ocean under ice, but very different villains. Our job is to decide which ending 3I/Atlas most resembles by listening to the accents in its light and letting the evidence talk in full sentences rather than bullet points. First comes the tale of tidal overdrive, a world living beside a heavyweight neighbor and getting flexed like a stress ball that never catches a break. For a long while, that flex keeps conduits warm and circulation lively. Then a resonance tightens, the wobble grows, and the heating spikes past the sweet spot. Fractures multiply, valves jam open, and the sea spends itself through vents that cannot resist an encore. The chemical accent of this fate is tidy and insistent. Prolonged venting strips the most skittish gases, while brines cook repeatedly against fresh rock and drift toward higher ionic strength. Chloride stays stubborn. Sulfur companions skew toward more oxidized partners born in overworked conduits, and the aerosol population trends smoother because frequent flashing favors near spherical beads. Polarization curves lean toward polite glass instead of jagged gravel. Organics survive the workout but come out trimmed, shorter chains with fewer delicate side groups, as if the vent cycle enrolled them in a molecular boot camp. Even the light curve obeys the metronome, with chemistry crests at predictable phases, and only small drifts. A drumline, powered by pain, yet proud of its timing, shifts scenes to migrating giants, where a massive planet ambles inward or outward and remixes orbits like a DJ with too much confidence. Our ocean world is not destroyed. It is marched through a gauntlet of near misses that jerk its path and torque its shell. Heating becomes stop, start. Some stretches are lively enough to throw parties. Others feel like the freezer aisle at midnight. The sea does not drain. It develops mood swings and keeps score in layers. During warm spells, sulfate hydrates and carbon-bearing salts precipitate and redissolve in alternating rounds. During lulls, pockets refreeze mid-argument and preserve whatever the last hot minute left behind. That rhythm yields a 2-flavor aerosol mix, one cohort with smooth skins from flash freeze, another with microfaceted textures from slow recrystallization. Polarization flips between bead-like and crystalline, depending on which pocket the spin has awakened. Ratios among alkali metals wander more than they should because plumbing depth changes with each thermal swing and samples different shelves of the pantry. Organics arrive in bursts tied to vents that woke after a nap, so the color slope wobbles by rotation and also by week. The spectrum reads like a travel vlog that keeps changing hotels. Within a single rotation, the story is coherent. Across many rotations, the baseline evolves as if chemistry remembers last week's schedule and refuses to pretend otherwise. Now the abrupt feature called stellar tantrums, when a passing star or a rowdy neighborhood encounter gives the outer system a shove. Our ocean world is tossed onto an escape track in one rude afternoon, astronomically speaking. There is no patient reheating and no craftsmanship, only a violent change of fortune. The lid thickens in the new cold, the sea retreats, and residual venting becomes punctuation rather than prose. The chemical accent here is raw. The brine keeps a formation-leaning mineral balance because the interior never got a final simmer. Early on, you expect a stronger release of carbon-friendly gas, a chloride to sulfate ratio closer to its birthright than to a repeatedly cycled broth, and aerosols that are texturally diverse, some beads from sudden decompression, many shards from brittle cracking as pockets freeze too fast. Polarization curves look messy and refuse to settle into a single family. Organics can be surprisingly intact, longish backbones with fewer sun-polished fragments because the chemistry saw less vent treadmill. The light curve is jittery. Chemistry peaks do not lock neatly to brightness. Outbursts show up like jump cuts in an indie film, and timing feels more chaotic than coy. Turning vibes into verdicts means comparing discipline, texture, sulfur mood, alkali ratios, organics, and the dance of color and polarization, but doing it as a story. If your chemistry is phase-locked like a military parade, if your aerosols prefer smooth beads, if sulfur looks thoroughly processed and organics are trimmed into pragmatic chains, you're smelling tidal overdrive. If your signatures stay coherent within a rotation, yet the baseline drifts across many rotations, if bead and facet alternate by longitude, if alkali ratios step from week to week and organics surge when specific regions wake up, then migrating giants are doing the choreography. If your signals flare without much loyalty to phase, if textures arrive as confetti with no single ruler, if sulfur looks underprocessed and organics keep their naive length, then a stellar tantrum probably wrote this chapter. There is a little epilogue written in motion. The way an object steers itself with jets can confirm the chemistry. Overdrive worlds advertise stable non-gravitational nudges aligned to persistent vents. Migration refugees show mismatched thrust vectors as new conduits awaken and old ones sulk. Tantrum cases feature thrust that appears during sporadic outbursts and otherwise leaves the path to gravity's quiet guidance. Kinematics is not the headline, it is the margin note that makes the headline believable. Of course, the universe enjoys blends. A moon can live through a migration error, flirt with overdrive, then catch a stray stellar side-eye on the way out. When paths overlap, look for incompatibilities that cannot share a single kitchen. You do not get relentlessly oxidized sulfur next to long-chain organics with naive fluorescence unless two regimes are interleaving in space or in time. Mixed fingerprints do not confuse the story. They add chapters and make the plot feel honest. The punchline is mercifully practical. Each eviction route prints a different boarding pass into the coma, which means a well-timed multi-night campaign can do more than admire a pretty curve. It can sort origins, treat the spectrum like a travel podcast with receipts, compare the snacks, track the layovers, and check whether the accent tightens or drifts as the world turns. Oceans can be homeless, yes, but their luggage tags endure, and if we learn to read them quickly, we can catch the next traveler before it vanishes into the dawn. Next, we pivot from forensics to engineering and sketch a nimble set of spacecraft that can sprint to a target, sip a plume without frostbite, and send us the recipe while the kitchen is still open. Chapter 16, Designing the Next Net. Designing the Next Net concept, missions, rendezvous cubes, fast flybys, and spectral samplers that treat interstellar visitors like pop-up restaurants. We sketch hardware that could sip a plume without getting frostbite. Catching an interstellar visitor is like trying to taste steam from a speeding kettle while riding a bike. The trick is not brute force, it is choreography. You need small, impatient spacecraft that can wake, aim, and sniff before the guest has finished clearing its throat. The classic deep space flagship is a symphony. What we need here is a jazz combo that can set up in the alley and still nail the solo. First up, the quick flyby taster. Think bus-sized brains on a toaster-sized diet. A compact bus with a chemical kick stage dozes in an inner solar parking orbit, then pounces when surveys flag a target. Solar electric propulsion handles the long slide to the intercept corridor, a short loud burn trims the geometry so the spacecraft swims along the coma's edge instead of punching through the hail. Instruments sit on a gimbal that can track independently, because the plume will not politely center itself in the slit just because we ask nicely. The payload is light but picky, a high-throughput ultraviolet to infrared spectrograph with rapid exposure cycling, a tunable laser spectrometer for key gases, and a dust mass spectrometer that can mouth-read single grains without breaking its teeth. Now the sipper arm. Imagine a folding boom that swings into the flow like a tongue catching snowflakes. At its tip, a cryogenic micro-inlet that skims gas at a few millibars above nothing, funnels it into a cold trap, and meters it to miniature columns. There, a microgas chromatograph separates flavors while a compact mass analyzer reads labels at high cadence. The whole chain rides on shock absorbers because space is quiet until it is not, and our inlet wants to taste vapor, not eat gravel. Thermal design is a magic trick. The tip should be cold enough to condense shy species, the plumbing just warm enough to keep them moving, and the detectors at their own fussy comfort zones. It is bringing oven mitts to a snowstorm and remembering which hand wears which glove. Dust collection, without drama, requires gentle hands. Aerogel worked wonders once upon a time, but at interstellar encounter speeds, even cotton candy hits like a philosophy exam. We cheat with speed control by flying down the flow rather than across it, shaving the relative velocity to something survivable. The collector uses layered aerogel with density that ramps from whisper to soft whisper, so particles decelerate without instant heartbreak. An electrostatic pre-filter upstream nudges submicron grains toward a deposition plate shaped like a record, letting us map capture time into radius like grooves of a soundtrack. Early grains near the center, late grains at the rim. This way, time history becomes literal distance, and our lab back home can drop a microprobe from noon to midnight with the turn of a stage. If patience and budget can stand a second act, send a rendezvous cube, a shoebox with ambition that drafts behind the main flyby like a pilot fish. Deployed a few hours before encounter, it carries a narrow field camera, a simple spectrometer, and a tiny cold finger on a stick. While the primary keeps safe distance, the cube dances closer, sampling microenvironments that change over kilometers. When it fills its two thimble traps, it flips and shields itself behind a Whipple plate made from stacked foils and aerated aluminum, then transmits the spectra and thermal logs to the mothership. If it dies a glorious, crunchy death at the coma's fringe, it at least dies chatty. None of this works without steering smarter than our reaction wheel's confidence. The plume breathes, the target rotates, and the density can jump by a factor that makes engineers use their indoor voices. Onboard autonomy must watch real-time histograms of count rates, compare them to do not fry me curves, and pivot between exposure modes without phoning home. A tiny neural leash guards the spectrograph slits against overload, the way a seasoned stage manager dims the lights when the crowd surges. Meanwhile, a hazard camera peeks ahead with a strobe and flags anything larger than ingredient headed our way. If it sees trouble, the boom tucks, the spacecraft leans, and we exit like a cat that pretends it meant to fall off the couch. Contamination is the invisible villain. Our samplers must not taste their own deodorant. That means bakeouts, witness plates, and a pre-launch diet where anything that outgasses gets swapped or shamed. We fly blank traps and open them far from the coma, then run the same sequence inside the plume. Subtract the blank, keep the flavor. It is culinary science with better hairnets. Data paths are designed like lungs. High-rate burst buffers soak up spectra during the hottest minute, compressing on the fly with lossless schemes, tailored to lines rather than pretty pixels. A downlink window on the outbound leg squirts the first look set, so ground teams can shout again, but shorter or again, but with the red channel wider to a second small set that is still inbound. Yes, this implies a pair of flybys leapfrogging the same object. because in this business, a redo is worth its mass in propellant. 2 quick tastes beat 1 long lament. Let us add 1 more toy, a standoff interferometer with a fold-out baseline. 2 little mirrors on a deployable boom create just enough separation to resolve fine structure in jets without growing a skyscraper. The interferometer watches the choreography while the sipper works the bar. Later, when we pair jet timing with chemical spikes, the depth puzzle turns into a solvable jigsaw instead of a Rorschach. And because opportunity likes to arrive on Tuesdays, the whole architecture needs a sleep light, wake violent posture. The spacecraft lives cheap near planetary waypoints, sipping sunlight and listening to survey alerts. When a candidate appears, a trajectory librarian coughs up 3 pre-approved routes. The flight computer chooses the one that matches propellant mood and thermal sanity, then begins a week-long stretch. Bake the collectors, cool the tip, rehearse the tuck and roll. This is fast food engineering that insists on clean knives. Would we dare bring anything home, not from an interstellar flyby? Not yet, but we can stash a sealed cartridge in heliocentric orbit for a rendezvous tug later, if capture conditions were gentle and the sample sings in situ. Future us can argue about budgets. Present us should at least leave a labeled cookie in the jar. Build it this way, and the next pop-up restaurant in the sky will not just smell salty, we will know the recipe, the oven temperature, and whether the chef likes to hum in minor keys. And when the check arrives, we will have already tipped the data pipeline. Next, we gather the threads we have spun, timing, chemistry, texture, and motion, and stitch them into a single tapestry, a portrait of the parent world you can taste from here. Chapter 17, The Planet You Can Taste From Here. The planet you can taste from here. We stitch the evidence, salt ratios, ammonia balance, isotopic tilt, seasonal jets. The conclusion lands. 3I/Atlas most likely came from a world with a long-lived, rock-fed ocean beneath ice. Insert satisfied gasp and 1 awkward high five. Lay the evidence on the table like puzzle pieces that refused to sit still until now. First, the salts, not a grab bag from random dust, but a measured duet. The chloride voice is confident. The sulfate harmony arrives on cue, and their relative loudness stays nearly the same across multiple spins once you correct for how much sunlight the vents are stealing. That steadiness hints at a reservoir fed from below rather than a surface pantry. Surface frost improvises, deep brine repeats recipes. The salt balance reads like a chef who has been making the same soup for centuries and still measures by instinct. Next piece, the ammonia balance. It does not shout, but it refuses to leave. Its features rise and fall with daylight like everything else. Yet the ratio of ammonia hints to water stays tighter than any mere frosting of volatile ices should allow. Mixtures that dissolve rock and calibrate their own acidity are stubborn creatures. They keep their antifreeze where it matters and release it in proportions that say, this is not a one-time thaw, this is a lifestyle. If water is the dependable colleague, ammonia is the colleague's charismatic mentor, always nearby to prevent disastrous meetings with the cold. Spin the board to isotopes. Heavy hydrogen and heavy oxygen pull at the corners of the story like hidden tabs. Their ratio does not match the accents of our local comet families, even after you account for how venting sorts the dancers. That mismatch is not a noisy outlier. It is a signature with posture. It suggests birth in colder nurseries, or storage under conditions that shielded the liquid from the kind of repetitive boil and chill our neighborhood bodies endured. Combine that with a modest spread between vents, some reservoirs more social, some more reclusive, and you get a portrait of layers, a deep stock that still remembers its first winter, and a shallower remix that added modern seasoning without rewriting the original diary. Now look at the motion of breath. Seasonal jets. The light curve waltzes with rotation. Yes, but over weeks the choreography slides as the object changes its angle to the sun. Some vents swell with maturity as the subsolar point migrates. Others settle, and the chemically rich ones are the least fickle. They act like veterans who have seen many springs. This is not a skin-deep performance, where a thin veneer steams and is gone. It is plumbing with momentum. When a vent continues to hum after sunset and rallies again the next afternoon with only a modest delay, you are looking at a channel connected to a reservoir with thermal memory and a steady stipend of ions. In human terms, the furnace is in the basement, and the landlord pays the bill on time. Take a step back. A world that can do all of this needs three things: a supply of energy that does not care about day and night, rock that speaks fluent ion, and a lid that saves more heat than it wastes. The simplest arrangement is a rocky core wrapped by a sea and sealed under an ice shell that has learned patience. The core whispers warmth from long-lived sources. Rock and water trade minerals until the liquid becomes a better traveler, less eager to freeze, more eager to carry. The shell traps the benefit and shapes where it escapes. Vents open where stress lines cross favors from the interior. Chemistry, like any good gossip, finds the fastest hallway and tells everyone. Even the dust agrees. When the brine-forward vents peak, scattered light behaves as though it is bouncing off tiny, well-rounded beads rather than broken shards. Those beads are exactly what you expect when liquid meets vacuum and turns to glass with a memory of salt. Organics join the show on their own schedule from different vents, but they do not perfuse the entire coma. That separation of roles argues against a single superficial frost party, and for a stratified interior, a brine layer that speaks with consistency and a carbon host that performs nearby, passing notes across the room. What kind of parent world would produce such disciplined exports and then fling them across interstellar space? One possibility is a moon once kept warm by a giant neighbor, its sea needed for ages, its minerals trained to circulate. Another is a compact shard from a deeper sea planet that split under stress, yet preserved the habits of its former home. Either way, you end up with oceans that learned persistence the hard way. They are not lakes of chance. They are institutions. If you wanted a single sentence with a firm handshake, here it is. The most economical reading of the data is that 3I/Atlas came from a body with a long-lived ocean that communed with rock, stabilized by antifreeze chemistry, sheltered by ice, and vented through conduits that remember yesterday. The salts keep time, the ammonia keeps house, the isotopes keep ancestry, and the jets keep score. The result tastes like endurance. There is a human moment tucked inside that conclusion. Somewhere, long ago and very far, a sea learned to balance itself against the cold and the rock. It flowed, it carried, it wrote in crystals and aerosols and patient ratios. Then gravity made a new plan, and the sea's courier left home. It wandered for ages without an audience, and finally drifted into our light, released a breath, and told us a story with no words. We listened with glass and math and a little humor, because even the universe appreciates a smile when the data behave. Cue the satisfied gasp, cue the awkward high five that misses the first time and lands the second. We will take it. The conclusion stands not because it is romantic, but because it is hard to shake. Change any one clue and the picture blurs. Keep them together and the image sharpens into a quiet, cold, durable sea. Next, we turn our attention to the message itself, what this salty postcard means for our wider expectations of oceans in the galaxy, and why a briny farewell can sound suspiciously like a welcome message in the brine. Chapter 18, Message in the Brine. Message in the brine. What this means: oceans may be common, chemistry familiar, and life less lonely than our apartment plants. We close on a quiet image, 3I/Atlas receding, leaving a salty postcard that says, "Wish you were here, water is fine." The lights are dim again, but the room is brighter for knowing. Across the monitors, a last sequence scrolls by. a soft decline in brightness, a narrowing of lines, the gentle hush that says our visitor is stepping off stage. It does not bow. It does not need to. It leaves behind the kind of evidence that keeps geologists smirking and biochemists hovering like seagulls over a picnic. The take-home is not pyro or spectacle. It is a practical sentence written in the dialect of ions. Oceans are not rare. They are a habit the universe keeps slipping into. It should not feel radical to say that, but our maps were raised on deserts. We drew dots for stars, neat ovals for planets, and assumed the in-between was dry and responsible. Then, a traveler from elsewhere wanders through and breathes a little winter perfume that somehow smells like old seas, and the scale shifts underfoot. If one system can cook a brine, cap it in ice, season it with rock, and then scatter a shard across the neighborhood, why assume that system is the show-off? Maybe it is the baseline. Maybe the real oddballs are the worlds that never learned to hold a secret ocean, like kids who skipped a rite of passage and grew up fine, but missed the stories. The comfort in that thought is not just water's persistence. It is water's behavior. It plays by rules we recognize. Give it a lid, a nudge, a patient source of warmth, and it will negotiate with rock until both parties sign a treaty. Hell, the same balancing acts that stabilize seas here, stabilize them there. The same buffers that tame acidity under our ice caps, tame it under theirs. The same chemistry that favors building blocks on Tuesday, favors them on Tuesday in a different star's time zone. Familiar does not mean easy. It means repeatable. The universe loves reruns with slight variations and strong character arcs. We are not declaring crowded galaxies of chatty neighbors. We are acknowledging that the stage is set in many places for interesting conversations to start. Oceans under ice are quiet theaters. They do not need sunburn to power their plots. They need patience, a few rocks that like to talk, and small sources of heat that never tire. If life is a skilled improviser, it can work with that. It has done so in basements of Earth where sunlight is rumor and chemistry is dinner. The leap from could to did remains a canyon. Still, the canyon now has more bridges sketched across it than we had yesterday. There is another message tucked into the salty postcard. Fragility is not the only story. We are trained to think of small worlds as brittle, of seas as temporary, of warmth as a fleeting gift. And yet, here is a traveler whose residues argue for stamina. Long practice can live inside modest bodies. Oceans can last without headlines. They can teach themselves to persist in cold, to travel well, to leave evidence that survives a vacuum commute. That is not fragile. That is stubborn in the best sense. A quieter implication is about time. Space often feels like an action movie, all collisions and speed. But the chemistry that framed this message is slow cinema. It took eons to steep. It took patience to tune. Everything about it whispers that the universe is not in a hurry to be interesting. It simply refuses to be boring. If we want more messages, we will need to adjust our attention spans. Quick flybys are helpful. Long listening is better. The cosmos likes to talk at the tempo of geology. Humor finds a perch even here. Somewhere, a tide under ice is making the same tiny complaint it made 1,000,000 years ago, and the complaint is productive. Somewhere, a pocket of brine is renegotiating with a patch of rock and winning on technicalities. Somewhere, a crack is practicing for the next afternoon's cameo in a jet. The universe is not serious. It is consistent, and consistency has comic timing. Cue the laugh track when a scientist writes definitive on a draft, and the next night Spectrum invents a new subplot. For us, the homework is obvious and doable. Keep the sky watched by instruments that do not blink. Build hardware that can sprint and sit. Train software to recognize whispers that resemble the ones we already decoded. Most of all, share. The message in this brine is not proprietary. It is a reminder that discovery is collaborative improv, not a solo recital. The more ears at the water cooler, the better the gossip. And then there is the human scene, the one that sneaks up at the end. The telescope slews to something routine, the team shuffles toward exits, and a few linger by the glass to watch the sky lighten. 3I/Atlas is already a rumor at the horizon. In the mind's eye, it pauses, turns, and drops a final note. Not a roar, not a flourish, just a signature. The balance of salts, the steady whisper of antifreeze, the tilt in isotopes that adds up to a sentence we can read now without squinting. Wish you were here, water is fine. If that message feels too sentimental, translate it back to the language of measurements and plots. You will get the same meaning, lines where they should be, shapes that track a patient interior, ratios that carry memory like a passport tucked into a well-worn jacket pocket. The poetry is optional, the evidence is not. What we learned is solid enough to lean on and light enough to carry into the next chase. So we file the data, pay the coffee debt, and start sketching new nets. Somewhere out there, another traveler is practicing its breath. We will be kinder listeners next time, quicker on the draw and slower to assume. And when the new spectra bloom, we will remember this chapter and smile. Because once you have tasted a planet from a single thread of light, you never again doubt what a whisper can hold. For the next chapter, let's widen the frame. A bonus epilogue on where to point our telescopes tomorrow morning, and which sky surveys will likely catch the next salty postcard. Or, if you prefer adventure, we can storyboard a first contact field guide for oceans we have not met yet.